Thank you, Celia, and thanks to the conference organizers for giving me a chance to talk about some of the work going on at Sandia and Lawrence Berkeley Laboratories and some of our partners. When Irfan and I got the invitation, we talked about what we wanted to present, and rather than just talk about the National QIS Research Center that we lead between Berkeley and Sandia National Laboratories, we thought it would also be useful for this audience to talk about the Testbed program that coincidentally has a testbed at Sandia National Labs and a different testbed at Lawrence Berkeley National Laboratories. And so what I want to do is just kind of sketch out a path where we go from current technology to understand what we need to make that next generation of technology. Okay, and before I start, I'm enough of a Sandia homer that I had to put up just a slide that talks a little bit about what we have at Sandia and the opportunities for people that may be looking for other opportunities. So Sandia has a program now that's more than 15 years old in quantum information science. We've got a very broad program that has a lot of depth in several areas. So we are particularly proud that we have working quantum devices in multiple technologies. So we pioneered the use of these surface traps for trapped ion quantum computing, and we supply them to research groups all over the world now. But we also developed silicon-based quantum computing devices, and we've got depth in neutral atoms, in diamond defects as well. Additionally, we do kind of all three pillars of quantum information science. We do quantum computing, quantum communications, and quantum sensing at Sandia. And we have a really great theory effort as well that has expertise in characterizing and benchmarking quantum devices and in estimating the resources required for high impact applications of quantum information science. And we have an email address, quantumjobs@sandia.gov, that if any of this grabs you, we're always hiring at some place in the program. So I wanted to start talking about testbeds. And so, one of the things that we've heard a lot about over the last few days is really amazing progress made by commercial companies like Rigetti, where is the previous speaker? Like Rigetti, like IBM, IonQ, Quantinuum, really are putting amazing test beds out into the cloud that people can use. So why do we need government test beds? Well, there are, so for one thing, building working quantum systems is expensive and complicated. This is something that is not available to most university laboratories. And one of the things that we're trying to do is provide some of the access you would have if you were putting this in your own laboratory to people in the community. And the issue is that commercial systems, although excellent, limit the ability to study the system itself oftentimes. You get compilers that make choices about what types of operations you're going to combine. You often can't change the pulses that go into them. And so what we're trying to do in the testbed program is provide as much as possible white box access to these quantum devices. And so, these are free to use. They give you access to lower level control. You can do advanced characterization and benchmarking techniques because you really have full access to what gates operate on which processors. You can change the pulse shapes and gate types. You can change the compilation strategies, and we've pursued all of those in the different test beds. So in the initial offering, the Department of Energy Office of Science, OSCAR office, started 2 test beds. The one at Sandia is based on trapped ion-based quantum computing devices, and the one at Lawrence Berkeley National Labs is based on superconducting devices. And the point is that each of these, as probably everybody knows, each of these platforms has different strengths and weaknesses. And in having multiple ones there, you can really investigate the field fairly fully. So trapped ions give you all-to-all communication, and they give you very high fidelity gates and very low crosstalk. In contrast, superconducting gives you much faster gates and much better control of those of what you're doing on those quantum states. I mean, a superconducting circuit is basically a control circuit. And they're also experimenting with other qubit mappings besides just qubits on this as well. So the Department of Energy has funded two very different platforms initially. So I'm going to talk about QScout first. QScout stands for the Quantum Scientific Computing Open User Testbed. This is based on trapped ions, trapped ytterbium ions in this case. Those systems use Raman lasers to do the 1 and 2 qubit gates in those systems. Currently, we've got a 10 qubit system that we're going to use for our second user time period. These are fully connected, so you've got all-to-all connectivity. We're getting more than 2 nines in the 1 qubit gates and almost 2 nines in the 2 qubit gates right now. So state of the art, kind of best of breed gates right now. And low crosstalk, low preparation and detection errors. We have our own programming language called Jackal, which stands for Just Another Quantum Assembly Language, and also indicates that Sandia spends too much time working on algorithms. Acronyms, sorry. And so why do we need another assembly language for this when there are things like OpenQASM available? Well, one of the things we wanted was real kind of control freak access to these devices. We wanted to know that we are, encoding qubit 1 on ion 7 and encoding qubit 2 on ion 13. And if we want to do 100 X gates in a row, we know that those, should compile away, to 0 operations. But for characterization purposes, we might actually want to run 100 X gates in a row. And so we needed really low level access to the gates, to where the qubits are in this device, so that we could really understand what's going on in that device. Similarly, we've got an open source language for the system on chip that does a lot of the electronic controls for these devices called Octet, and that's exposed to a Jackal package called Jackal-PAW, which stands for pulses and waveforms. So you can now start to change the pulses that go into the 1 and 2 qubit gates that you're performing on these as well. We are hoping to build up to 32 qubits on this and to get higher fidelity gates and to be able to do things like partial measurement along the way for algorithms that need that. So the way QScout works is we work on the computer for a while, and then we have a user period where we call for proposals, and we then support those user proposals on the device. And the first round started earlier this year, and we had 4 groups that used this. The University of New Mexico looked at non-stochastic Hamiltonian simulated on this. Indiana did some work in quantum dynamics, so not just ground state quantum chemistry, but looking at proton-coupled electron transfer reactions. Oak Ridge looked at connecting low-level characterization to algorithmic performance issues. And Berkeley campus looked at randomized analog verification methods on this. So that was the first period. We've now accepted proposals for our second user period, and we've got teams from the Applied Physics Laboratory, from Lawrence Livermore National Labs. We've got 2 commercial companies this time, which is kind of fun, Supertech and IBM, and the London Center for Nanotechnology, and another proposal from Indiana. So if you're interested in using QScout, we are about to open our third call for proposals. We're going to have multiple calls per year. You can look at qscout.sandia.gov for more information about that, or email qscout@sandia.gov. And it's a relatively painless process, a 2-page proposal to get access to those times. And we've got a multi-institution team of people that reviews those then. So the Advanced Quantum Testbed is the testbed at Lawrence Berkeley National Laboratories. They've got some similarities and some differences. Theirs too is a unique quantum resource. Like QScout, when you get time on one of these machines, you are working with the team that actually implemented the machine. So they'll help you interpret your circuit, best map it onto those resources. One of the really unique things that the Advanced Quantum Testbed has that QScout doesn't have is a testbed is a collection of different quantum processors. You can put multiple chips down in a dill fridge. They have their main one, which is based on our Transmon, but they have the opportunity to develop new qubit devices and experiment with those as part of their user access process as well. They've done some really great work in advanced quantum compilation and control in conjunction with Joe Emerson, now at Keysight. And they also, another real notable aspect of this is they both developed their own quantum control software and hardware, but they also work with additional industrial partners for that as well. So you can test out different ways of controlling those devices. So like I said, the current chip is an 8-qubit Transmon chip. They've got that in a big Blue Force dilution refrigerator with 160 RF lines going into it. Like I said, they've got multiple control options for that and a kind of open programming stack for that device as well. So they just finished their first user time. They had 4 national laboratories, 2 companies, and 1 university in their first time for that. And the call for proposals is open again. In this first time, they had Lawrence Livermore, Supertech, and a team from Sandia working on various projects, among others. And similarly, if you're interested in time on the Advanced Quantum Testbed, there's a website here. I think the amount you have to prepare for an AQT proposal is even shorter than the QScout proposal. I think they just want like a paragraph or something. And that's at aqt.lbl.gov. Okay, so we already got an introduction to the National Quantum Initiative and what the DOE's trying to do with these larger centers. So like we just heard, there was a National Quantum Initiative Act in 2018. President Trump signed this as like the last thing before the government shut down before Christmas 3 years ago. And in that act, it had funding opportunities for the National Science Foundation, for NIST, and for the Department of Energy in that. And what the Department of Energy did in this is fund these 5 centers that we heard of. And so, as you heard, we've got centers for Brookhaven, led by Argonne National Labs, Fermilab, and Oak Ridge National Laboratories. And I'm going to tell you a little bit more about the system that Lawrence Berkeley and Sandia run that's called the Quantum Systems Accelerator. So the Quantum Systems Accelerator is really focused around quantum computation. In this effort, we're not really looking at communications or sensing, although many of our partners are also interested in those. We have a really incredible team that is a part of this. We've got people like Will Oliver, who spoke earlier at this meeting from MIT. We've got people like John Preskill from Caltech. We've got Misha Lukin from Harvard. We've got Chris Monroe from Duke, Jun Yi from Boulder, Ivan Deutsch from University of New Mexico, Peter Love from Tufts, Scott Aronson from University of Texas. We have a really remarkable team working together on this. And the goal of this team is to be able to kind of, so we use this mountain metaphor, once you've given this metaphor like 30 times in presentations, it sounds really, really cheesy. But for those of you who haven't heard me go through this, the image here is that we know we want to get to fault tolerance at some point in the future where we know we're going to have multiple applications for quantum devices. But when you're hiking in the mountains, sometimes you don't see the path up to the high peaks until you're standing at the tops of one of the foothills. And so what we want to do in the Quantum Systems Accelerator is stand atop NISQ hardware, noisy intermediate scale quantum hardware. So as might be exemplified by the test beds that I just told you about, or by the commercial offerings. And then we want to take steps forward in various directions where we push the limits in number of qubits and fidelities of qubits in the architecture that interconnects those qubits, and then understand what kind of impact does that take us. We don't know the right path to get from here to get to here, and so we're going to be wandering all through this. But what we want to be able to do is make some prototype devices that really start exploring this middle range. And so apologies for the eye chart here. These are the processors that in our first generation we're really trying to push the envelope on. So let's say for superconducting systems, one of the real challenges has been increasing the connectivity of this. And so one of the things we want to be able to do in superconducting systems is develop 3D integration pathways where you can do more than just neighbor connections between the qubits here. And what we'd like to be able to do is make a demonstrator that has 16 qubits, but has something like all-to-all connectivity in those superconducting devices. Similarly, ions, so normally when you build ion traps, you make a long chain of those ions, and the longer the chain, the more unstable it can get. One of the things that we'd like to be able to do is think about ways where we can break up that chain into shorter chains and couple those together by either shuttling ions back and forth or by coupling them using entangled photons. Neutral atom quantum computing, I think there's a session this afternoon, is really seeing an exciting renaissance due to these reconfigurable optical tweezer arrays. And so we would like to start doing maybe not quantum simulators, but things like analog emulators using neutral atom-based devices that really start pushing the numbers up to exciting areas like 200 atoms. So in order to make that work, we have this full stack of science and technology that goes from material science characterization and optimization to looking at how that impacts various qubit platforms. I mean, one of the things that sets the QSA apart is we've got 3 different platforms that we're focusing on here: superconducting, ions, and atoms. And then understanding how we engineer controls with those devices to make them as reproducibly programmable as we can to these processors that I talked about, and then to kind of understand algorithms that can run on these that tell us things like, well, when are these doing something that represents quantum supremacy? What types of optimization algorithms can we do on these devices? And more to the point, are there opportunities for specialization? Is one of these platforms, let's say neutral atoms, really superior for a particular simulation algorithm or a particular optimization algorithm? And by having multiple platforms available, we can start to explore optimizing algorithms for those platforms themselves. So we are already seeing, again, as with the other centers, we're just getting started on this. We are already seeing publications show up that are starting to move the needle in terms of what we can do here. So I talked about the way Sandia looks at building larger ion trap computers where we make linear chains and couple them together. The other approach out of the Bollinger group is to use a penning trap to trap a kind of 2-dimensional crystal of those ions. And in this initial publication, they're just using that to do electric field sensing and displacement sensing of those ions. So you're using kind of collective modes of this 100-ion crystal to do quantum sensing applications. The real challenge with this will then be, how can you get enough individual control into those devices that you can start to do computation in those geometries. Something that was published a couple months ago in Nature by the Lucan group at Harvard is this example that I mentioned about how neutral atom quantum computing is really seeing a renaissance right now. And so the real Achilles heel of neutral atom quantum computation has always been that when you load these devices, you don't get loading atoms in every site. And so what they do now, I mean, it seems trivial. I mean, it's easy for me to say, but they just drop the optical tweezers that don't trap any atoms and then rearrange them so they can get close packed arrays of those, so that you know you always have neighbors around you. This is an example by the Lucan group that takes, I think it's rubidium atoms, makes a 256 atom close packed array of those, and in this case, they use it to do a simulation of an Ising model on this. So 256 atoms is pretty good in terms of the number of qubits one has, and so you can do analog simulations of Ising type models for this. They've also explored other types of lattices other than just square lattices, and some of the topological properties that arise from that, and whether you can use those properties to do things like encoding logical qubits, let's say, to kind of take two different topologies, this is 0 and a 1 state. The other area that we're excited about is work coming out of the Simons Institute at University of California. And Celia, this touches on your question about to what extent can you get quantum-inspired algorithms that are classical and surpass what we had? And so, the big example of that has been density matrix renormalization group that actually came from chemistry and then jumped back and forth between the matrix product state and back to density matrix renormalization group. This is a variation on that called the rigorous renormalization group. And one of the challenges in some of these methods is that as you go through difficult points in those simulations, like going through a phase transition, density matrix renormalization group often has really terrible behavior going through those points. And what's unique about this approach is that you get smooth behavior as you go through topological points or critical points in the phase diagram. So, like the other centers, one of the big areas that we're also interested in is not only building the technology that's going to take quantum information science forward, but also building the ecosystem that's going to kind of, create a field and create a workforce around those technologies. So we are very interested in engineering engagement. We've got a number of close partners. One of the things that we're doing that a lot of the centers are not doing is looking at how we can incubate startups as well. So I think if you talk to people who have run large hubs for the Department of Energy, one of the things that they say is the best interactions they have are with the startups that emerged from those research efforts. And so one of the things we want to learn how to do is how do you incubate startups, how do you support them, which technologies do you develop, and so on. We all here believe that quantum is going to be a big deal, and that we're going to have a quantum industry that's going to require a quantum workforce. And so one of the things that we're very interested in is how do we develop a quantum workforce, not only in the kind of top universities that already know about quantum, but a lot of other places that like let's say junior and community colleges that quantum's a newer topic to, but then still could have training programs that could provide really amazing jobs for our people in various aspects of quantum information science. And then finally, there is a challenge as we're building a new workforce that we want this workforce to be diverse and inclusive. And something that is a constant concern of ours is that as we're building this new field, that we're building that field in a way that is reflective of our nation. And so with that, oh, and if you are interested in this, my email address is here. David Kiston's email address. David is in charge of the quantum ecosystem in the center. Jake Douglas is also here from the center today. And with that, I would thank you for your attention. I probably have a little bit of time to answer a question or two. And so thank you very much.
Thank you, Rick. And I think we do have a minute or two for questions before the break. Very exciting what you're doing.
Anyone, you believed everything I just said? Questions?
Testbeds.
So did you say the Jackal was just another?
Just another quantum assembly language.
Jackal another, and you could have had a recursive one?
Oh, yeah, that would have been good.
Right.
No, I'm not going to give them that idea. Like I said, Sandia probably spends too much time coming up with cute acronyms. Yeah.
How open are you for international collaboration in quantum development?
So open, but we haven't pursued much of that so far. So we do have a collaborator at University of Sherbrooke. So we have foreign members of the center, and we of course have foreign graduate students and the like. You know, this past year has been this flurry of standing up this big center and getting IP management plans in place, and so you know, we're just getting over the hurdle of you know, how we're going to do industrial collaborations, and so you know, I think in any of these projects we'd be interested in international collaboration, and we do in the QSA have an international coordination board that has people like Tommaso Calarco and other people on it to kind of make sure that we're well coordinated with international efforts, and so we don't, you know, kind of overlap things that people have already figured out, and that we can work well with them. I think what we hear from our international coordination board is that good intentions are not enough for international collaboration, and that if the DoE really wants to do this well, they're going to have to get, you know, targeted funding for collaboration between our centers and international centers. But right now, what we have are good intentions.
What about the testbeds?
Testbeds, I think we are open to that. I don't believe we have gotten proposals so far from those, but I mean, as the program manager of one of them, I'd be interested in seeing proposals from international sites as well. Sorry? Yeah. So, you know, if people are interested in submitting, I mean, again, these are still small test beds, you know, 8 to 10 qubits, but you really do get, you know, the goal is to provide as close to the metal access to those as you can get. So as close to having it in your own laboratory. You know, we're not there, but you can do you can make your own pulses. So.
Well, thank you very much, and if you have further questions, come up and see Rick. We have a half-hour break, so come back. 2 more presentations starting at 11:30.